There's a few slides from this week's lecture that we still need to cover. We were discussing statistical power, which is the chance that you identify an effect if there is an effect. And the question is then, so how can we increase power? Well, power is determined by a number of factors. First of all, the effect size that you want to be able to identify. That is basically your alternative hypothesis. So you want to test what the likelihood is that you are able to identify an effect, if there is an effect, and this effect is assumed to be, for example, 1 or 5% or what have you. Then it holds that the larger this effect size that you want to be able to identify, the higher your statistical power is. And that should make sense. It's easier to identify a huge effect than a very small effect. A very small effect, as is shown here, it's a needle in the haystack. A small effect is difficult to find. So where do you get this effect size from? How do you know whether, for example, the effect size that you want to be able to identify is 1? Well, it can be based on previous literature or from experts in the field. They may be able to tell you what a reasonable minimum effect size is that you want to be able to identify with your study. Now, how can you get a larger effect size? Well, by having a huge treatment dose, right? So people do not get sort of half a course, but a full course, or a very strong incentive, not €1, but 100 euros. And you may also want to pick a study group with subjects that you know to respond fairly strongly to a treatment. Now, in this graph, I show you why it makes sense, why a larger effect size increases your power. You're basically shifting this curve around the alternative effect to the right here. So we're only looking at sort of one side of the test that we conduct. And yeah, so power being this green area that I showed you earlier, and here, so the green area clearly grows. So here, by shifting that curve out, so by saying that you want to be able to identify a much larger effect, power goes up to 80% rather than the earlier 30%. Okay, so that's effect size. Effect size is a major determinant of statistical power. Secondly, power is determined by how much variation in the treatment you have in your data. Now, in a field experiment, that is pretty much given, right? So the default is 50% get treated, 50% is then in control. But in observational data, that may vary. And obviously, the less variation you have, for instance, only a small share of the population that you are looking at has been treated, the lower your level of statistical power. Now, that's basically the standard deviation of the treatment variable. And how do you get it? For example, there's some old data from earlier years and from before doing your study that gives you some idea of variation in treatment. So that's a second determinant of power. A third one is how noisy is the measurement of your outcome. Outcomes are often measured in various ways. For example, say that you're interested in ability, and then you may look at course grades, or you may look at an intelligence test or what have you. But those are all noisy measures, right? So all outcome measures tend to be noisy, but some are more noisy than others. and the more noisy your outcome measure is, i.e. the larger the standard deviation of your outcome, the more difficult it is to identify an effect. So the more difficult it is to find a signal in all this noise. Now, how do you get an idea of the noisiness of your outcome measure? Well, you may actually, it may actually be around. So maybe this outcome has been measured for some time already, so you can use historical data. But it may also be that you do a trial run, you want to do a field experiment and with a certain outcome measure. So you start measuring the outcome already so that you have some idea of how noisy your outcome measure is. And then have some idea of the statistical power of your study. An obvious determinant of power is basically alpha. And the level of statistical significance that you use. Well, we don't usually play around with that, right? So we just set it at 5% and that's it. Now, and then the final, and within the context of this lecture, most important determinant of power is sample size, and because that is something you can do something about. Obviously, and the smaller the sample you have, the more difficult it is to identify an effect. So, if you want to have lots of power, you had better increase the size of the sample that you are working with. That should make sense. If you look at the graph here, so here's the curves for the alternative hypothesis and the null hypothesis, and the more observations you have, the higher those curves become, and with smaller samples they become flatter. But here you see, with lots of observations, you can be more precise, and then the green area showing your level of statistical power goes up. Say that you do a field experiment, for example, for your master thesis, then what should N be at the minimum? Well, that is called power analysis. So basically, you take all of those other things, all the determinants of power as they are. So your outcome measure, for example, has a certain noisiness, and you take alpha to be 0.05, etc., etc. Then what should your N be to have a power of, for example, 80%? And so basically what you do is you specify alpha, the power that you want to get, the effect size that you want to be able to identify, and the noisiness of your outcome variable, and then you can compute what the size of your sample should be at the minimum. The great thing is that R can do that for you. We do that with the package Power, and you'll get some practice in computer assignment 2A and 2B. This is actually the formula behind all of this, if you're interested. Then, finally, power and null findings. It may be that you want to know and also want to show the readers how likely it is that the effect that you estimate is actually negligible. It may be that you do not find a statistically significant effect, but that may also be due to low power, right? So if you just have a low power test, then it's very likely that your p-value is huge, right? So, but how are you then going to show that no, it's not that I have low power. I have a huge sample. I measure my outcome very precisely, etc., etc. What this study tells us is that the effect of this treatment is likely to be negligible. Now, what you then do is a so-called equivalence test. You basically take two steps. First, you qualify what a meaningful effect is. and that's shown here in the graph. So say that you think, well, a meaningful effect size should be at least, it's called eta plus here, so say 2%. And since we're always doing two-sided tests, so it's between +2 and -2. So whenever the estimated coefficient, well, the interval around it is bounded within this region, -2 and +2, then we say, well, this is really negligible. But it may also be that your estimate is fairly imprecise and that it also covers here H0. H0. So in that case, you cannot conclude that you really estimate, you really find that the treatment effect is close to 0. Now, how there's a way of going about this. That's by step 2. So you conduct 2 one-sided tests. Is it smaller than epsilon plus, so say 2%, and is it greater than the -2%? And if both tests give you a statistically significant result, then you can indeed conclude that the treatment effect that you estimated is negligibly small. Dill and Kruger is actually a study. Well, they would have benefited from doing this. They actually do it in a more qualitative manner. They basically say, well, following a private college doesn't do much in terms of later earnings as soon as you adjust for ability. And they actually also discuss this in the paper. All right, that's it for now. Well, I'll be seeing you next week.